So this is going to be our conservation of momentum equation that we're going to use from this point forward. All right, so let's suppose we have a thread that holds a 1.5 kilogram cart and a 4.5 kilogram cart together. After the thread is burned, the compressed spring that's between them pushes the carts apart, giving the 1.5 kilogram cart a speed of 27 centimeters per second to the left. So the question is, what's the final velocity? What's the velocity of the 4.5 kilogram cart? All right, so we're going to use our conservation momentum equation. That's mass 1 times initial velocity 1 plus mass 2 times initial velocity 2 equals mass 1 times final velocity 2, or final velocity 1 plus mass 2 times final velocity 2. Well, first of all, both of them are not moving initially, so the total initial momentum is going to be 0 because 1.5 times 0 plus 4.5 times 0 gives me a total of initial for 0. Afterwards, the 1.5 kilogram mass is moving at 27 centimeters per second. Convert that to meters, and that gives me 0.27. Now, we give it negative because it's moving to the left. We have to incorporate that direction anytime we do conservation momentum because the direction does matter. So with that being said, 1.5 times negative 0.27 gives me negative 0.405. And then the 4.5 times the final velocity 2, and final velocity 2 is what we're looking for. So we take the 0.405 to the other side, make it positive, divide by 4.5, and we get 0.09 meters per second. Now what you notice is your final velocity of the second car is going to be 9 centimeters per second. Now, if you think about conservation of momentum, the momentum initially was 0 because neither car was moving. So the momentum after also has to be 0. So if the first car has a momentum that is 1.5 times 27 centimeters per second, you can figure out mathematically, but think about it like this. If the first mass is 1.5 kilograms, the second mass is 4.5 kilograms, that means the second mass is 3 times the mass of the first one. Well, if it's 3 times the mass and has to have the same momentum, then that means it has to have 1/3 of the velocity. So if the velocity of the first car is 27 centimeters per second, then 1/3 of that will be 9 centimeters per second. So it goes along with what we were talking about with conservation of momentum, that mass times velocity will give you your momentum, and each one's going to be equal and opposite because the total in the initial was 0, so the final also has to be 0, with one being positive and the other being negative. In this example, it says car 1 of mass 6 kilograms is moving at 3.5 meters per second and collides with car 2, the mass of 4 kilograms, that is initially at rest. Car 1 moves off at 0.7 meters per second, the same direction as its initial velocity. All right, so car 1 is initially moving 3.5 meters per second, comes in and it hits car 2. Car 1 initially at 3.5 ends at 0.7, so it slows down. Car 2 initially at rest, so it has an initial velocity of 0, and then starts moving off at some velocity that we have to figure out. So we use our conservation of momentum equation. Go ahead and plug in our numbers. The 6 kilograms is the first car times 3.5, and then 4 kilograms times 0, that's the initial velocity of the second car. So 6 times 0.7, that's the final momentum of the first car, and then the final momentum of the second car is 4 times the final velocity. So you put these in your calculator, you get 6 times 3.5 gives me 21, and that's going to give me 0, so I get a total of 21 on the left-hand side. And then 6 times 0.7 gives me 4.2. So I'll subtract 4.2 from both sides, it gives me 16.8 on the left-hand side. Then I divide by 4, and that gives me a total of 4.2 meters per second for the final velocity. So you can see that the final velocity of the second car is going to increase as the final velocity of the first car decreased from its initial velocity. Now, something you should notice is that the final velocity of the second car has to be greater than 0.7, because if for some reason the first car has a final velocity greater than the second car, then that means the first car would have had to gone through the second car, which is not possible. So we were expecting something greater than 0.7 for the final velocity of the second car. In this example, it says that a 35-gram bullet strikes a 5-kilogram stationary piece of lumber and embeds itself in the wood. The piece of lumber and the bullet fly off together at 8.6 meters per second. So what's the original speed of the bullet? So we're trying to look for the initial velocity. All right, so we got our conservation momentum equation. We got all the information given to us. We got 35 grams, which needs to be converted to kilograms. So mass 1 is going to be 0.035. And then the second mass is 5 kilograms. Initially, for the second mass, it has 0 velocity because it's stationary. The final velocity of the second mass is going to be 8.6, and the final velocity of the bullet is going to be 8.6. So we'll go ahead and plug in the information that we know. We know that 0.035 is going to be the mass of the first of the bullet times its initial velocity, which is going to be our unknown, plus 5 times 0, that's the initial velocity of the piece of lumber, so that's going to be 0. And then 0.035 times 8.6 and plus 5 times 8.6, because the final velocity of both of them when they stick together is going to be the same. Now, something to keep in mind here is I get a lot of people who say, well, this bullet stops when it hits the piece of lumber. Actually, it doesn't. When the two stick together, that means they're moving together. So you have to include the bullet with its momentum as it's moving forward. All right, so you punch this in your calculator, you get 0.035 times 8.6, that gives you 0.301, and then 5 times 8.6 gives me 43. Then we add those together, we get 43.301. Then we divide by 0.035, get our initial velocity is 1,240 meters per second.